Good day, students. We are going to begin our discussion of the F block metals, which is topic C, the very last topic on your course outline. Two of these lectures will be in the form of recorded PowerPoint presentations, and then the final one we will do as a the final two, sorry, we'll do as a face-to-face class on the coming Friday, and the online class next week, Monday. Now, this material is broken up into basically three parts. The first part where we talk about give some basic understanding of the F block metals, and then we move on to talk about oxidation states or stable oxidation states, and also the electronic spectra and its uses. And finally, we talk about how we prepare or separate extract and separate the lanthanides and actinides, and also how we calculate the magnetic moments and compare that to the experimental data on magnetic moments or magnetism in these types of materials. In this section, we'll be covering the definition of lanthanides and actinides, so we're clear on that. We also will talk about lanthanide contraction and its consequences. First of all, if you look at your periodic table, and this is the ACS Chemistry for Life periodic table, you would see two things. You notice that after barium and after radon, we have a group, and it doesn't follow from barium to hafnium, tantalum, etc. There's a group in here. It's sort of a reddish color on your screen and a greenish color, and you can see that elements 57 to 71 are there and 89 to 103. This group on the top is called the lanthanide group, and this one is called the actinide group. Of course, the first member of the series is lanthanum. The first member of the series below is actinium. And these materials are sometimes called rare earths because they're rare, because we can't extract them in large amounts and they're not found in large amounts. Some of them, of course, are not observed directly in natural deposits in nature. Some of them are actually observed because of chemical reactions. And as we would see, they're a very special group of materials. So they fall in between here. When we refer to first row transition, we refer to these from over here, from scandium to zinc. When we refer to, and this is of course 3D, 4D, and 5D metals, if you hear me refer to it, so you know what we're talking about. Of course, note that the platinum group, which is basically iridium, platinum, gold, rhodium, palladium, silver, etc. This group of metals here do not behave like the lanthanides and actinides, right? Even though you might think, well, it looks like it's in the same period or very close to it. So they're sometimes called the F block metals. F block because the 4F and 5F subshells have electrons in it. And we define them broadly as metals which have the N-2F subshell filled with the last electron. So what we're saying is that if we count, let us say in the first row of the transition metals, we have 3D, and of course we have 3D, then we have 4S, 4P, 4D, 4F, etc. When we reach the point of having 4D and after D we get F, we're really supposed to go to 5S, etc. And what we're saying is that the subshell that is 2 down from the ultimates, the last shell is actually filled in this case. So in the lanthanides, we see the 4F is occupied as lanthanum, and in the actinides, the 5F shell is occupied. And formally, some of these don't fall into that category. For example, like lanthanum doesn't really fall into that definition, but formally it is defined as such. So the general formula is given here. You might need to make a note of this in case you need to work out the electronic configuration for yourself. But as well, on these lecture materials, and you could print this out and keep this as a crib sheet or a sheet you can look back at all the time. We have the elements here given. and look at the configurations. Of course, XC means that we're writing shorthand, right? So whatever it's the configuration for xenon up to that point. We have the 6s 5d2, so this is why I said lanthanum is not exactly in that, because there are no 4f electrons here. And you can see from the other ones that this is the n-2 shell, this is the n-1, and this here is the N. So this is the so-called ultimate shell, which is the 6s. Of course, the 5d lies above the 6s. We know about that from the first transition, why that happens. But here is the 4f. Now the 4f, as you will see, is written like this because in fact the 4f shell is below in terms of energy the 6s and the 5d. And you can see how the filling goes here. They fill from 1 go down, but of course the difference here is that in cerium the electron that would make this F2 is actually in D, right? So that is why the formula did have mention about the D before. And so you need to make a note of the filling of these electrons, and that some of them actually have the same number of F electrons even though they have different atomic numbers. So for example, here you can see that Y you can see here that deuterium and lutetium both have 14 electrons, whereas in this table here, europium and gadolinium both have 7 F electrons, right? So the difference really is if the D shell is also occupied. In a similar way, the actinides follow the same convention as well. It's a little bit more tricky to fill out with the actinides, of course, radon shortened form, so up to that point, and then we have the filling of the electrons. And again, we have the same thing as before. For example, nobelium and lawrencium both have 14 F electrons. Of course, this one has 7s and this is 7s2, but 61, so the D is filled in that case, right? And so it follows the same pattern as we saw before. Now, the lanthanide contraction is what is responsible for this sort of filling, and it refers to a consistent reduction in size, that size of the atom or the ion, with increasing atomic number. You may think, of course, that for some periods, as I increase the atomic number, I do have a reduction in size, but it's not consistent, right? And so we'll see in the graphs I will show in a minute why we say it's a consistent reduction in size. There are two other things to note here, that if we take the size of the first member of the lanthanide series and the first member of the actinide series, and we compare them to the element that comes before it on the periodic table, we'll see a huge reduction in the atomic radius, right? So if we take barium and radon and compare them to lanthanum and actinide, we'd see that. And you should take some time to go and look that up so that you can cement in your mind that the lanthanide contraction results in a decrease in the atomic or the ionic size. Of course, the question will be why. So let's look at these F orbitals. These are the shapes of the F orbitals, and many aren't familiar too much with the shapes, so I put them on the material for you to see. And if you think about these shapes and think about the electrons that are in shells above it, namely those electrons that will be in the S and D shells above it, let's think about an electron that's going to be in an S shell, a 5s or a 6s shell, and how that electron may be found in space and time versus the electrons that are in these shells. We can see that these shells are not probably very good at shielding that electronic charge. So let us say I have a 6s electron, a 5s, and it's a spherical and it's around this F that's a Z cube. I can see that there are many parts. There may be many parts here that would not be shielded if I were to find electrons. For example, if I found an electron there, or there, or there, or there, it's not shielded. And so actually, we observe this lanthanide contraction because the shielding effect of those F electrons, remember this is the N-2 subshell, aren't very effective. So they aren't good shields for stuff that are beyond it. And therefore, the effective nuclear charge increases as we go across the period. So the number of protons, of course, is increasing, but that positive charge from that proton is felt more and more as we go across the period, because the shielding of those left electrons to each other and to things which are beyond it isn't very good because of the shape of those orbitals, right? And of course, that means, therefore, that the size will of those atoms or ions will decrease consistently as we go across the period. That, of course, has other implications, which we'll talk about in terms of the reactivity and the chemistry of these materials. So here we have two plots, one of atomic radius in picometers versus the atomic number, and here's the ionic radius of the 3+, 2+, and 4+ is not too popular, but we'll talk about that in another bit of material. And we can see here that we start off with lanthanum, we go down, and there is a decrease in size. Now, there are two that pop out here that people use, and this is also a little debatable because these two actually have a filled or half filled. So this is a 4F7 state filling, and this is a 4F14 filling. And actually there is supposedly some sort of stabilization that occurs when you have this fully half filled or fully filled state. Of course, some will comment that the numbers given for the atomic radius here are really in terms of the covalent radius and not single metal atoms in terms of a metallic radius. So there's some debate about that, but generally you can see that the size of the atom decreases gradually. And here's actually even better plotted when we think about all of the 3+ states of these ions. You can see here this is a gradual and consistent decrease, right? So if we measure from there we see that this decrease, if we take between each of these points, it's about the same each time, and that is because the effective nuclear charge is increasing in the same manner between each successive element, right? And of course, this therefore means that these ions are, although they are larger, for example, than the transition metal ions, it means that the charge that is spread over these ions, these ions are larger, and then the charge, of course, because it only normally goes up to +3, means that that charge to size ratio is very different from the transition metals. So there are some consequences. The first is that the second and third root transition metals have comparable size to these materials, lanthanides and actinides. So they have similar size, but the charge is different, and of course the chemistry will be different. There's also a challenge in terms of separation, because of this contraction, they tend to have the same stable oxidation states, unlike some of the other ones we've seen in the transition metal chemistry, and they're also of the similar size. So therefore, we will think that their chemical properties are similar or comparative. And separating one of these metals from the next would rely on us having different chemical properties to do so. So in the pure state, partitioning one from the next is actually difficult. But we could use some other properties like the ability to be hydrolyzed or ion selectivity, etc., to separate lanthanides from each other and lanthanides from actinides. The electronegativity shows a slight increase across the period because of that, and also electric potential, so a small regular increase across the period. These increases are actually quite small, and so these properties cannot really be used, for example, in separating one group of lanthanides from the next in a mixture, but they can be used for some technological applications. Because of this contraction, all members of the series have high density. So the number of grams per centimeter cube or kilograms per meter cube is actually quite high, and some people might refer to it as being heavy because of that, but really we're really talking about the density in that case. So a large amount of it occupies a relatively small space because of that contraction. Another property that is very important for the chemistry of these materials is basicity. And if we think in terms of basicity of, let us say, sodium hydroxide or potassium hydroxide, we must remember that that OH minus ion has to be available to do its work. So the more ionic that material is the more that in, for example, in aqueous solution, that OH minus would be available to do its job as a base. In the case of these metal hydroxides, these lanthanides and actinides, we see that the size of the metal ion decreases as we go across the period. That also means that the covalency of that metal OH bond increases. And of course, as the covalency increases, it means therefore that the OH minus ion is not as readily available. Those electrons are going to be really tied up in the bonding to the metal ion, which is small and charged, and therefore the basicity is going to decrease across the period. So for example, if we go from lanthanum to CHEM, we see that the basicity increases greatly from the left to the right of that period. It also means that the oxides become less basic as we go across the period, and the stability of those materials becomes better as we go across the period. So the materials, as they become more covalent in character, that's the oxides, nitrates, hydroxides, etc., they become more stable. And the propensity to be hydrolyzed, that means to break up into its constituent ions in aqueous solution, decreases. So the first member of that series, you can hydrolyze it, you can dissolve it, but the last member you can't, for example. And finally, we're going to talk about the complexes and complexation. And the first thing we learn is that it's not easy to form complexes with these metals as it would be with the 3D or 4D transition metals. And this is really because of one thing, as the size of the ions are very much larger than 3D and 4D. Remember, we are much further down in terms of periodic table, in terms of the atomic number here. The size of the ion in relation to the charge on the ion, remembering that the +3 state is most stable, is actually relatively small. And therefore, those ions do not have the driving force to make large number of different types of complexes. And we observe that atoms, ions like fluoride and oxide, which are relatively small but also strong, good sigma donors, pi donors, for example, are much preferred over things which are larger and sigma donors are pi acceptors like CO and Cn minus, etc. Of course, the coordination chemistry is not so restricted that we don't have examples of things outside the norm. And in these cases, we see that we have a number of coordination numbers that are available. In fact, all of them are available up to coordination number 12. So, for example, yttrium, when bonded to acetonate, which is a ligand that bonds through 2 of the oxygens, and with water, that complex, which is stable, actually has a coordination number of 7. The cerium version has a coordination number of 8. The neodymium one, a coordination number of 9. The last cerium nitrate, actually, the coordination number is 12 because the NO acts as a bidentate ligand, binding through nitrogen and also through oxygen. So 6 of them by 2 bonds each gives us a coordination of 12. Right? So although they don't form too many complexes or as many complexes as we would have observed with the 3D and the 4D transition metals, they do form complexes. They tend to want to be bound to oxygen and fluoride-based ligands. To a lesser extent, of course, chlorine, iodine, and a much lesser extent, chlorine, bromine, and a much lesser extent, iodine-type ligands. But when they do so, they may form complexes with very large coordination numbers. So to recap, you should be familiar with the definition of lanthanides and actinides, how we fill those orbitals and write out the electronic configuration. That's very important. And what is the lanthanide contraction, why it occurs, and at least 3 to 4 consequences of that will influence the chemistry of these materials.